Hey guys, this is Mr. Gagnon again, and this is something you definitely want to watch to completion. We're going to tie together a lot of these concepts that we've learned here in the energy system, the energy unit, in one single problem. And this is going to be kind of important when you're going to look at the test. I'm going to give you a test pretty soon on this stuff. When you look at the test, this ties together a lot of the concepts that we've done. So I'm going to work this one problem out. We're going to call it tying, or tie it together. Okay, so I'm going to present to you guys a problem where we have a roller coaster, okay, hill, okay, and then there's a loop out to the bottom. So I'm going to give you three spots. I'm going to give you the A spot, the B spot, and the C spot. And as we know, that's the radius of the loop. Okay, so let's pose a question for you. Okay, the question is, let's say I have a roller coaster cart right here. Okay, and that roller coaster cart is going to start going down the hill. Let's assume there's no friction, okay, because friction will affect the little details of this problem. Let's say I've got a mass of the cart at, let's just say it's 1,000 kilograms. So it starts from rest from point A and then goes down and around the loop and then out here. So we hope we're going to get out here. Okay? We hope it's going to end here. Point A is located at a height of, let's say, 100 meters. Okay? Above its lowest point on the track. Okay, the car rolls down the incline and follows the track around a loop, the radius, which equals 30 meters. That means half of this height is 30 meters. Okay, radius, 30 meters. Now, this is a thinking question because it's going to ask you we'll ask you a bunch of questions. All right, so the first few questions will be simple, and then we get a little more difficult as we move along. Okay, the first question: how much work energy is needed to get the car up to that point? Okay, so how much work? Now, we know that work is force times distance. Now, unfortunately, we don't have the force of gravity with gravity on this car yet. So let's figure that out. Okay, we'll call it the force of weight, which is mg. The force of weight is mass 1,000 times gravity. Okay, so the force in this situation is the force of weight, and it's going to be 9,800 newtons. Okay, so the work required to get this up to the top of that, okay, is now simple because work is our force times the distance or the height. and then 4 zeros. So the first question was how much work's needed to get that to the top, and it's the answer is 980,000 joules to get this up to the top. Now, that energy is pent up in potential energy. Okay, so we know that potential energy, sometimes we call it GPE, is equal to mgh. And that's actually what we did. We did the mass times the gravity times the height, and we got the potential energy of 980,000 joules. Okay, so the second question we say is, what is the speed or the velocity at point C? Okay, so here's when we start having to look at how much energy is available to us. So we know that the gravitational potential energy is 980,000 joules. That's available to us. We want to know the velocity here. So as it goes down, it transfers the gravitational potential energy to what we call kinetic energy. Okay, so the kinetic energy at the bottom of that hill is equal to the potential energy at the top. So the kinetic energy at the bottom is equal to the potential energy at the top because we took all the energy from here, the height energy, and we moved it down to velocity. So this is a situation where kinetic energy is equal to 980,000 joules. Okay, but we know the formula for kinetic energy is 1/2 mv squared. Okay, so 1/2 mv squared is equal to the potential energy here. Okay, so if I go and I solve for this, I'm going to get rid of I'm going to divide out by the mass because I know what the mass is. I think it was 1,000. So that's going to get rid of that. And it's also going to get rid of 3 of the zeros. So 1/2 v squared, we just get rid of the mass here because the mass is 1,000. 1/2 v squared is equal to 980. Okay, and dividing by 1/2, v squared is, this is the same as multiplying by 2. So when we have 980 multiplied by 2, the answer here is 1960. Okay, get rid of the square. Okay, and then we find the square root of 1960. And we come up with 44. Okay, so at the bottom here, we've transferred the potential energy down to the kinetic energy, and we came up with a velocity of 44 meters per second. Now, so here's the thing. This is without friction, so friction would slow this down a little bit. But this is like a frictionless surface, kind of like a perfect situation. Take a look at that, and you may want to write that down. Okay, so here's where we start having to think a little bit more because now we get the velocity at point C here at the very bottom of that thing. Now we're going to have to find the velocity at point B. Okay, so if you really think about it, okay, the radius is 30 meters here, which is halfway up. So if I double that, okay, the diameter is this times 2. So the diameter is going to be radius times 2. Okay, so the height or the new diameter at B is 60 meters. All right, so that's kind of an important concept to realize, that this goes back up. Okay, we're assuming it's going to stay up there. Okay, but it goes back up, and we need to know the velocity at this point. Okay, so now let's use our thinking abilities here. Okay, well, the height is 100 meters. We know that there's a total energy. Okay, energy of 980,000 joules. We know that's the case. So we know that the 980 is equal to the kinetic energy plus the gravitational potential energy. Okay, we know that because these two have to add up to 980. Now, up here, there's no kinetic energy, so the gravitational potential energy ends up being the 980. Down here, there's no gravitational potential, so the kinetic ends up being 980. But if it's at this point, 60 meters above this point, 60 meters. Now, I chose the number 100 for a reason, because we can use percentages with this. But like, we can pretend that the car is, number one, 60 meters above where it started. So let's look at this for a second. 980 equals kinetic energy plus gravitational potential energy. Okay. Now, let's see what we've got here. Again, 980 mass was 1,000, right? V squared plus 1,000, 9.8. That's our gravity. The new height is 60. That's the little key point right there. So let's figure out what this is. We'll do a little bit of calculations. So let's clean it up a little bit. Okay, 500 v squared plus 1,000 and joules. Okay, so I'm going to bring this 588 over here. I'm going to subtract it from both sides. So it's going to be 980,000 minus 580,000. Okay, what I'm left with, okay, I move this over here. I'm left with 400,000 joules is 500 V squared. Okay, so with not much room left here on the bottom of our screen here, okay, I'm going to solve for V. So let's find a spot like up top. I can just kind of move this over. I'm going to stick it right up here so we can come up with our velocity at B. So 400,000 equals 500 V squared. Okay, so divide that out by 500. So I've got 800 is V squared. Okay, square root that. Okay, I got 28.3 meters per second. So all I had to do was just know that there's a total of this much energy in the system. We know that that equals the kinetic energy plus the gravitational energy. It's got a little bit of both, right? It's got a little bit of height here, It's gonna have a little bit of speed here, or velocity. So we just have to know that we can use the formula to come up with the answer of 28. Okay, at the top of that loop, right there, it's going 28.3 meters per second. Not based on like rotational dynamics, but just based on the height of the thing. Okay, you didn't have to get into any of that, A is v squared over r stuff. You just had to know based on the height of that thing. Okay? So this is an example, guys, of tying it all together. We're tying together our gravitational potential energy. We're tying together our kinetic energy, okay, through this system. Okay, it's just a matter of thinking and getting yourselves into an idea of where you're thinking of different situations. Now, I'm going to give you one more to look at and ponder. This involves springs as well. So I'm going to tie all this stuff together with springs, and we're going to take a peek at that one. Okay, so we're going to tie this together. Okay, with springs. Okay, so here's our roller coaster. Down. And at the bottom of the roller coaster, we're going to have a spring. Okay. Let's actually say that the roller coaster starts here. So this doesn't need to be included. Okay. So tying it together with springs, we can kind of look at the same situation. So I'm going to put this cart here. Okay, and we're going to say the cart's going to go down the hill. Again, friction is negligible here. We're not going to look at friction so much. It's going to go down the hill like this, and it's going to compress the spring some distance. Okay, so let's see what's going to happen here. Let's say the cart, mass of the cart is 1,000 kilograms. Okay, I'm going to ask you, let's say it's 100 meters high. Okay, I'm going to ask you basically to think about what's going to happen when that cart hits the spring. It's going to go shrink up, and then the spring's going to go pew and shoot it back up. Now, in a frictionless system, that spring should shoot that cart back up to the top. But we know that doesn't exist. So let's figure out how much energy is available here. Okay, we actually, from the last one, we know that potential energy, or gravitational potential energy, is mass times gravity times height. So the available energy at the top, GPE, is 1,000 kilograms times gravity. Now you might be wondering why I'm not putting gravity as a negative number here. We're looking at just the absolute value of the energy available here. And we could call it negative and call it negative energy, but let's just keep it in as an absolute. Height, okay, 100 meters. Now look, GPE is 980,000 joules. Now that energy is going to be turned into what right here? So I'm going to ask you, like at point B, what is the energy here? And you'll be able to answer because you know that we transfer from gravitational potential to kinetic, right? Kinetic energy. So we want to know, like, if I give you a spring constant here, okay, how much that spring will stretch or compress in this case, given the amount of energy here. So it's as simple as this, guys. So we're going to say that the gravitational potential energy has the potential to stretch a spring with the spring energy, half kx squared. Okay, remember, x is the stretch distance, k is a spring constant, and this is our energy that we calculated already. So I'm going to turn it around a little bit. I want to say that this spring stretches or compresses 1.2 meters. Okay, I'm going to put that up here. I'm going to ask you to calculate the spring constant of that spring if it only compresses 1.2 meters. So let's take a look. GPE, which is 980,000 joules, is equivalent to half K is what we're looking for, 1.2 squared. That's our compression distance. So if I just do a couple simple calculations here, okay, so 980,000 joules is half K times 1.44. Divided by half times 1.44. Okay, so 980,000 divided by 0.5 divided by 1.44, okay, equals 136.1111. Okay. Okay. Equals K. So we know that this is newtons per meter. So huge K value, right? That spring's going to be pretty hefty duty spring to be able to handle that and only stretch or compress 1.2 meters. So our spring constant's here. And guys and girls, there are springs that have a spring constant this high. Okay, they're just very, very large. Okay, so that's how to relate GPE to elastic potential energy of a spring. Okay, it's all involved in taking energy and just saying it just shifts. It doesn't get used, it actually just shifts. And in a perfect world, this would bounce back all the way up to the top. Now, at point B, I could also ask you, like, how fast it's going at that point, right before it touches a spring. And you could come through and say, well, the gravitational potential energy is equivalent to the kinetic energy, and you could solve it like that. Okay, and I'm not going to go through that solution with you. I'm going to let you handle that. But we already know a number for this, and we know the formula for this. So I'll set it up. MGH equals half mv squared. Okay, and you can solve for v at point B. Okay, so that's tying this all together. Guys, I know this was a long video, but it will be a big help to you with your test on this.